Okay, this is the next video, Unit 6 review. This is part 2. Now we're going to talk about when things start rotating. So, when do things start rotating? Well, really, that's when we have a net torque. Right now, we're not going to be worried about net torque. So yes, you need a net torque to angularly accelerate. So if you're at rest, you need a net torque to start rotating. Let's not even worry about that right now. Really, we're going to look at rotational kinematics. Just like I said in my kinematics video, rotational kinematics doesn't really care about the torque and stuff. It doesn't care about mass, doesn't care about that stuff. It's just predicting motion based off of the variables like acceleration, velocity, displacement. So how does rotational kinematics work? Well, if we had, let's say we had a bar, right? Okay, so for rotational kinematics, we learned from Crack the Whip that each part of this thing is moving at different speeds, right? They're each moving at different velocities because each point is taking the same time to travel a shorter and shorter distance. Okay, and that makes a lot of sense. But then it becomes really hard to do kinematics because they're each moving at different velocities. So if things start accelerating, they each have different accelerations. How do we make this easier on ourselves? That's where we got to start introducing rotational kinematics. Each point is going to take the same time because they're moving together and they're going to travel the same distance. They're going to complete one rotation in the same amount of time. So they travel the same angle. They sweep out, no matter what, they sweep out the same angle. Like this swept out the same angle as this. That's what we call rotational displacement. So I'll say change in theta is equal to rotational displacement. So I'll just say rotational displacement. That's like how much angle you sweep out. There's the way to figure out. So let's say you know the radius, right? To figure out how much distance you've traveled, you have to do change in theta, or you're gonna have to do distance. Or wait, is it distance or displacement? I think it's distance, not displacement. No, wait. Is it displacement or distance? I have to think about it. Because your displacement is going to be like this, but then your distance is like how much you travel. So I'll say displacement, because in most cases you're not really dealing with arcs anyways. Displacement is going to equal your change in theta times r. So it is distance, and the reason I know it's distance is because if you have 2 pi, like if this is 2 pi, that is going to be one full rotation, and then the distance is just 2 pi r. That's just your circumference, right? That makes sense. So obviously, if you did one full rotation, your displacement is 0 because you end up at the same spot, but the distance traveled is going to be 2 pi r. I have an extensive video on like explaining like the bridge equations. You can find it somewhere. It's probably at the start of my channel because I made this channel with Unit 6. So I have an extensive video explaining this very well. What I'm going to say, just to save time, is that so displacement is equal to theta over r. Now rotational velocity, right, v, or that's your linear velocity, is going to be equal to your rotational velocity times r. So each of these things have the same rotational velocity. They rotate the same amount in the same amount of time, so they have the same rotational velocity, so as your distance gets bigger, your linear speed gets bigger. And then as you can imagine, we have acceleration equals alpha times the radius, or the distance from the axis of rotation. So those are the kind of bridge equations. Those are the way we can go from linear to rotational. So that's really useful, because if you have like a bike rolling, you have the wheel rolling of a bike, right? We can figure out that its linear displacement, right? It's going to be proportional to how much it has rotated. It's rotational, and it's proportional by the radius. So if you have if you have a bigger radius and you rotate the same amount, you're gonna have traveled the same amount of distance, which kind of makes sense. Like if you had a small like toilet paper roll and you had a tractor, if each thing rotates one rotation, the tractor is gonna have rotated way more, or displaced way more. Not it's rotated the same. So that's how the bridge equations can explain that. Let's kind of get into now. I'm just looking at my notes. I talk about. I guess we can just get into rotational kinematics. Because of these bridge equations, all of our old like change in x equals 1/2 alpha t squared plus omega times, oh, I already started using the rotational versions. All of our old like kinematics equations, x is equal to 1/2 at squared plus velocity times time, we can just plug in the rotational version. So we can say change in x is just change in theta equals 1/2 alpha t squared. The reason we can do this actually has to do with the fact that when we measure the theta and the omega and alpha, we do it in terms of radians. And once again, I have a video explaining it much more extensively. But because of radians, we can actually like do this basically. Like everything works out the same. Actually, I don't even think it has to do with radians. It might just be because like math and stuff. The point is you can just substitute in all your rotational versions. Everything works out the same. You will get like the correct numbers with the time. There's no rotational version of time. I don't know. Maybe ask Einstein about that. So there's more. Obviously, there's more rotational kinematics equation. Omega squared equals omega initial squared plus 2 alpha times change in theta. So my advice is just practice. Practice doing some rotational kinematics problems. There's all sorts of problems, and something annoying is sometimes they'll say this bike has traveled 2 meters per second in 5 seconds, and it angularly accelerated by this much, and then you have to kind of keep switching between linear and then rotational. That's where your bridge equations are useful. So rotational kinematics conceptually, that's kind of it in terms of trying to understand stuff. We gotta talk about, let's talk about rotational inertia. I think rotational kinematics is pretty straightforward. Just use your equations. It's just linear kinematics, and there's also graphs, and they work the same way as rotational kinematics or linear kinematics. If you're having trouble with rotational kinematics, chances are you're probably having trouble with linear kinematics. So just practice and try to make sure you understand the problem-solving strategies. Write down your variables, what you know, what you're trying to figure out. Draw a picture, and then I think that should be there in terms of, rotational kinematics. Let's talk about rotational inertia and Newton's second law for rotation. So we did the windmill lab, and what we figured out with the windmill lab is that with the windmill lab we had the masses and stuff. So we had like the windmill, and then some of the masses were closer in. I'm going to just give a brief summary of the windmill lab. What we just figured out is that it's harder you're going to get less rotational acceleration if your mass is closer in. If your mass is farther out, if your mass is closer in, you're going to get more angular acceleration. If your mass was farther out, you're going to get less angular acceleration, even if the mass was the same. So we realized, okay, that's interesting. So torque net is proportional to angular acceleration. That's the first thing. Yes, torque net is proportional to angular acceleration. What that means, is the proportionality symbol just alpha? I think it is, right? Because like torque net is proportional, that's a proportionality, to alpha. Okay, whatever. Torque net is proportional to alpha. What that means is if you have twice the net torque, you have twice the angular acceleration. That's kind of similar to force is proportional to acceleration. Twice the force means twice the acceleration. So maybe there's some connection to force equals mass times acceleration, or F net. So what we realized is that, yes, no matter what, torque net is proportional to alpha. If your rotational, and if your mass was farther out, right? Even if the mass was the same, you're gonna get less angular acceleration for the same amount of torque. So if we had like a graph like torque versus alpha, or alpha versus torque, you could see that if you applied a certain amount of torque right here, this group gets very little alpha compared to group 1. And group 1 had mass closer in versus group 2. So what is the deal with that? Why does the same mass result in less angular acceleration if the mass is farther out? That is a key principle behind rotational inertia. Rotational inertia is all about how hard is it to angularly accelerate something. So if if your mass is farther out, you have more rotational inertia. It is harder to angularly accelerate it. And just like how force is a rotational, or torque is a rotational version of force, alpha is a rotational version of acceleration, your mass is really just rotational inertia is just a rotational version of mass, how hard it is to linearly accelerate something. So we got this equation, torque net equals I alpha, or alpha is equal to torque net over I. And it's just Newton's second law of rotation, very similar to the linear version. But rotational inertia, just things to keep in mind. It really depends on 4 things. First of all, the mass. So if I had this little rod here, right, I can like kind of angularly accelerate it like this. If it had more mass, yeah, it's going to be harder to angularly accelerate it. The shape matters. So wait, shape, was it shape? Yeah, shape. So we'll call it shape. Shape can deal with distribution. Like if this had the same mass, but then you had these, like, I don't know, these maybe a bone shape where you had like these bulges or something, I don't know. You can imagine there's more mass on the outside compared to the inside, so it's going to be harder to angularly accelerate. The size matters. So if this was much bigger, yeah, it'd be harder to angularly accelerate it like that. And then the axis of rotation matters. So if I had a bunch of mass here, you can imagine if you had all that mass, it'd be very hard to angularly accelerate it. But if I changed that, so instead of rotating from this axis, if I was rotating from this axis, all the mass is at my hand, it's going to be very easy to just rotate the thin rod. Axis of rotation matters too. In math problems, that's something you have to really think about. For any math problem, they will give you the rotational inertia. The rotational inertia for a point mass, so for like a point mass here, is equal to m times the distance squared. We call that torque is equal to mr squared. Okay? Or sorry, not torque. I'm so sorry. I. Inertia. If you have more mass closer, it's going to be less than that. So if you had a hoop, it's just a bunch of point masses, and you can do the calculus to figure out that for a hoop, it's just mr squared. For a disk, it's going to be 1/2 that. So yeah, and then for like a sphere, it's going to be, there's some mass closer there, so it might be 2/5 or 3/5 or whatever. They'll give you that. You don't have to remember that. For a rod, axis of rotation matters. If it's here, the rotational inertia is different than if the axis of rotation was here. It's kind of weird. It's not an intrinsic property of the thing. Like what I mean by that is like mass of an object is just the property of the object. It just has that mass. Rotational inertia, well, it is a property of an object, but it's not like an intrinsic, tangible thing. Like it depends on where your axis of rotation is. It's not like it can change. This axis of rotation has a different rotational inertia than this axis of rotation, then this axis of rotation. So it's pretty cool stuff. Really, what you got to know is what can you do with it, right? So if you had, where's my green marker? I want my green marker. If you had torque net equals I alpha, if you have the I and you have the torque net, you can figure out the alpha. Stuff like that. So So there's also some problems with like figuring out the alpha. I'm gonna go over two pretty common ones. Just to kind of end off this video. How long is this? I don't think this would be that long. I didn't actually need to make a part 2. I didn't realize that. Oh, 15 minutes. Yeah, okay. It's good that I made a part 2. So, for torque, like some common problems can include a pulley. So hopefully we can do pulleys. I know we had a rotation cumulative, so I don't know why I drew that. We had a rotation cumulative, so this isn't like too like foreign. But if this mass is bigger than this mass, if this has like a rotational inertia, like before it didn't have any mass, so we just kind of did that. But now this has rotational inertia, so it's going to angularly accelerate. So if it accelerates, we need a bigger net torque on one side. The distance is the same, so if torque is equal to force times distance, if distance is the same, more torque means more force. In other words, we need more force on this side than this side. So this force is going to be equal to that force, this force is going to be equal to that force, and then we have our Fg. So that is kind of something to keep in mind with pulleys, right? When things are angularly accelerating, the tension is not going to be equal on both sides because it has to angularly accelerate. It has to have a net torque. So yeah, that's pulley. I don't know why I said it twice. There's also rolling. So for rolling, you got to think about, well, what is the torque that is going to cause the rolling? Well, so for rolling, there's going to be, if the axis of rotation is the center of mass, Fg doesn't produce a torque, neither does Fn, because Fn is going to point directly towards the axis of rotation, so there's no angle, essentially. The only other torque that could cause this to rotate is force friction. And regardless, I kind of drew that wrong, regardless if it's rolling up or down, friction always points up. Now here's why. If it's rolling down, the omega is this way, and it's speeding up, so the alpha has to point in the same direction. That's just a kinematics idea. If acceleration and velocity are in the same direction, it speeds up. Same thing applies rotationally. So we need alpha in this way, which means we need a torque in this way, because torque net is proportional to alpha. If you want alpha in one direction, torque needs to be in the same direction. So you can imagine if the torque is this way, we need a force pointing up to cause that rotation. And what's kind of counterintuitive is the same thing works the other way. If omega, if it's rolling up, omega needs to point this, or omega is rolling this way, so alpha needs to point in the opposite direction to slow down. That is the same direction as before, where the torque still is in the same direction as alpha, so the friction still points up. So rotational inertia applies here, rotational inertia applies here, right? Because if now, rolling is a whole other thing, and I don't know how in depth I want to go into it, because it's kind of confusing. Because if you have less rotational inertia, it's easier to angularly accelerate it. So if you think about what's going to win, a hoop or a disc on the same ramp, disc is going to win because it has less rotational inertia, more angular acceleration. But then if you think about, okay, it has more angular acceleration, so it has more angular acceleration, so it has more linear acceleration, because the two are connected, right? If you think about alpha equals a over r, right? It's just a bridge equation. More a means more alpha. So really what that means is that, okay, so more alpha means more a, because the radius is the same. So if you think about F net, ma is going to equal mgx, so fgx, which is mgx, minus, or mg sine theta, I'm doing gx, but yeah, sine theta minus force friction. M is the same in both cases. Let's say disc and hoop have same mass. So this is going to be the same. In order to get more acceleration, you need less friction. Which, I mean, makes sense, right? To get more acceleration, you need less friction. So therefore, the torque on the disc is actually less, right? It's actually less torque. But it also has less angular acceleration, and less torque because it's less friction. So it has less rotational inertia, but it still has more alpha because the rotational inertia decreases way more then the torque decreases. The overall angular acceleration is bigger. A very similar thing can be said about if you had a meter stick with a mass on top versus a meter stick with a mass on the bottom, which one would drop first? It seems like this should drop first because it has a greater torque, right? Greater distance. But it also has greater rotational inertia because the mass is farther out. Which one's bigger? Well, if you think about torque is equal to I alpha. So force, gravity times R is going to equal mr squared, or like some fraction of that. The R is squared. So if your distance doubles, sure, you have twice the torque, but you have 4 times the angular or rotational inertia. I think that's where I'm going to leave it off here. I don't remember any other key points. It's really just boils down to practice. Can you derive the linear acceleration for this? Can you derive the linear acceleration for a system like this? And it's really practicing how to apply the conceptual parts of that. So I really encourage to practice. Thank you for watching. I'm going to do Unit 7 tomorrow, and I'll try to find time to upload everything. So yeah, thank you for watching.